Welcome to G Fun Facts Online. Today, we are bypassing the usual pleasantries to dive straight into a technological paradigm shift that is currently rewriting the rules of computational physics. We are talking about the convergence of artificial intelligence and quantum computing. Specifically, we are looking at AlphaQubit, a breakthrough system developed by Google DeepMind and Google Quantum AI. To understand why this is a pivotal moment in history, we first need to understand the battlefield on which this war is being fought. That battlefield is defined by a single formidable enemy: noise. In the classical world of computing, the silicon chips inside the device you are using right now, information is robust. A bit is a 0 or a 1. Physically, this is represented by high or low voltage. If you shake your laptop, or if the temperature in the room fluctuates, or if there is a slight variance in voltage, your computer generally does not care. It knows that a 0.9 is meant to be a 1 and a 0.1 is meant to be a 0. This stability is the bedrock of the digital age. But in the quantum realm, this stability vanishes. Quantum computers rely on qubits, which operate on the principles of superposition. A qubit isn't just a switch. It is a complex wave function that can exist in a linear combination of 0 and 1 simultaneously. This allows for exponential parallel processing power, but it comes at a terrifying cost. That wave function is incredibly fragile. It is susceptible to what physicists call decoherence. A stray photon, a vibration from a truck driving by outside the lab, or a microscopic fluctuation in temperature can cause the qubit to collapse. We call these errors bit flips or phase flips. In a standard computer, an error might happen once in a quadrillion operations. In a quantum computer, the best physical qubits today fail about once every 1,000 operations. You cannot build a reliable supercomputer with components that fail that often. This is the fundamental bottleneck of the industry. For decades, the solution has been quantum error correction, or QEC. The strategy is redundancy. You take a single logical piece of information, a logical qubit, and you smear it across a grid of many physical qubits. This is often arranged in what is called a surface code. If one physical qubit in the grid gets hit by noise and flips, the others hold the structure together, and you can fix it. But here is the catch. You cannot look at the qubits to check for errors. In quantum mechanics, if you measure the data qubits, you collapse their superposition and destroy the calculation. You have to check them indirectly. Engineers place intermediate sensors called ancilla, or stabilizer qubits, between the data qubits. These stabilizers ask the neighbors, "Are you all aligned?" without asking, "Which way are you aligned?" The result of these checks is a stream of zeros and ones called the error syndrome. Imagine a massive control board of lights. If everything is working, the lights are off or stable. If an error happens, a specific pattern of lights, the syndrome, flashes. This brings us to the decoding bottleneck, which is where AlphaQubit changes everything. Receiving the syndrome is only half the battle. You have to interpret it. You see a flash of lights, and you have to deduce, mathematically, exactly which qubit flipped so you can send a pulse to correct it. This is a massive inverse problem. Standard decoders, like the minimum weight perfect matching algorithm, or MWPM, treat this like a graph theory problem. They look for the simplest path that connects the error dots. They assume errors are mostly independent. But in real hardware, errors are rarely independent. A cosmic ray might hit the chip and wipe out a cluster. A control line might be slightly over voltage, biasing a whole row. Standard mathematical decoders miss these subtle, correlated relationships. This is where Google DeepMind entered the chat. Their hypothesis was brilliant. What if we treat the stream of error syndromes not as a math problem, but as a language problem? Humans are bad at seeing patterns in high-dimensional noise, but neural networks excel at it. AlphaQubit was built using the same architecture that revolutionized natural language processing, the transformer. Think of models like GPT or Gemini. They use an attention mechanism to track relationships between words in a sentence, even if those words are far apart. DeepMind realized that quantum errors behave just like words in a sentence. There are spatial correlations. An error here affects an error there due to crosstalk. And there are temporal correlations. An error that happened 3 microseconds ago might influence the syndrome reading right now. AlphaQubit utilizes a recurrent transformer architecture. It receives the syndrome data over multiple time steps. But it does something standard decoders cannot do. It ingests soft readouts. In a standard decoder, the input is binary, 0 or 1. But in the actual quantum processor, the measurement is an analog voltage signal. It might be a weak signal, indicating only 51% confidence. A standard decoder forces that to a 1 or 0, throwing away that nuance. AlphaQubit takes the raw analog data. It sees the confidence levels. It uses an internal memory state, thanks to its recurrent neural network layers, to track the history of the system. It doesn't just apply a rule. It develops an intuition for the chaotic static of the quantum world. So how do you train an AI to understand quantum physics? You cannot just run it on a quantum computer initially, because collecting that much data is slow and expensive. And you don't always know the ground truth of what error actually happened. DeepMind used a 2-stage rocket approach. First, they used a digital simulator. They generated hundreds of millions of samples of quantum noise. This taught the AI the grammar of the surface code, the basic rules of topology and error chains. Once the model was pre-trained, they moved to step 2, fine-tuning on the Sycamore processor. They exposed the model to real data from the actual quantum chip. This is crucial because every quantum chip is unique. It has its own defects, its own crosstalk patterns, its own specific calibration drifts. By fine-tuning, AlphaQubit learned the specific accent of the Sycamore chip. It learned to predict errors that simulators couldn't even model. The results, published in Nature, were staggering. They tested AlphaQubit against the industry standards. Against the fast MWPM decoder, AlphaQubit achieved 30% fewer errors. In the world of exponential scaling, a 30% reduction is the difference between needing 1,000,000 qubits and needing 500,000 to do the same job. But even more impressive, it beat the tensor network decoder. Tensor networks are complex mathematical models, often considered the theoretical limit of accuracy. AlphaQubit beat them by 6%. Why? Because tensor networks usually assume the noise follows nice, clean statistical distributions. AlphaQubit learned the messy, non-Markovian reality of the hardware. It also solved the problem of leakage. Leakage is a nasty type of error where a qubit jumps out of the computational basis entirely. It goes from a 0 or 1 state to a 2 state. Standard codes are blind to this. They try to correct a 0 or 1 error and end up introducing more damage. AlphaQubit, during its fine-tuning, learned the spectral signature of leakage events in the syndrome history. It could spot a leakage event and compensate for it. To prove this wasn't just a fluke on small grids, they simulated AlphaQubit on distance 11 codes, massive grids of 241 qubits, and the advantage held up. This has profound implications for the roadmap to fault tolerance. We operate under something called the threshold theorem. It states that if we can get physical error rates below a certain threshold, we can correct errors faster than they happen, and we can compute indefinitely. AlphaQubit effectively raises that threshold. It means we can tolerate dirtier, noisier hardware and still get a working computer, because the software is smart enough to clean up the mess. It shifts the burden of progress from hardware physics to software intelligence. However, we must remain grounded. There is a catch, and it is a big one: speed. Superconducting qubits operate in the gigahertz range. A correction cycle needs to happen roughly every microsecond. AlphaQubit is a large neural network. Running a transformer takes time, milliseconds maybe. If the decoder is slower than the quantum computer, a backlog of errors builds up and the system crashes. This is the latency bottleneck. Right now, AlphaQubit is a demonstration of accuracy, not speed. The next phase of research is distillation, shrinking this giant brain down into a tiny, fast student model that can run on specialized hardware, like an FPGA sitting directly inside or next to the cryostat. We are not looking at a magic wand that instantly solves everything, but we are looking at a proof of concept that validates a hybrid future. The distinction between quantum computing and artificial intelligence is blurring. Future machines will likely be hybrids, a quantum heart beating within an artificial neural brain. The AI will calibrate the controls, design the circuits, and decode the errors in real time. AlphaQubit has shown us that quantum noise is not just random chaos. It has a structure, it has a language, and thanks to deep learning, we are finally learning how to speak it. That is the detailed breakdown of AlphaQubit. It is a dense, complex topic, but it represents one of the most significant leaps in our journey toward the quantum age. We are moving from the era of brute force physics to the era of neural-guided quantum mechanics.